It's about to start, we'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound, check. Camera, check. Lights, check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hi, I'm Leandro Facchinetti and Happy New Year! Let's write some code together, shall we? And what we have on the menu today is actually several things. So, first of all, an update on the bug that we found last week on the stream, our last stream. We found this bug with out-of-bounds access in the memory, crashing REAPER. And in case you're new here, we are writing real-time audio effects for REAPER. That's... Bo is here. Hello, Bo. Great to have you. And yes, you are on time. You caught the beginning of the stream. Right, so we are writing real-time audio effects for REAPER using this language called JSFX. And today we are going to explore a different language. We'll get to that in a moment. But first, we reported this bug in the JSFX language. If you tried to access memory out of bounds, it crashed REAPER. Not just crashed your effect, it crashed the whole digital audio workstation, which is kind of crazy, right? That shouldn't happen. And in fact, it was a bug. And I reported the bug on the stream last week. And in about 45 minutes, Justin replied saying that, it will be fixed, and he already knew what the issue was and why it happened in certain architecture. So I thought that it was some update that crashed things because we got an older version of REAPER, and in that older version, the bug was not happening. It turns out that when I was getting the older version of REAPER, I got the Intel version because back in July, the ARM version was still in beta. But it turns out that the problem was the architecture. So even if I went to REAPER 630, which is an older version from July, and I got the ARM version, the M1 version, that would have crashed as well. And the crash had to do with assembly instruction in ARM that is branch greater than or equal to. So it's essentially an if-then-else kind of statement, but in assembly. And I believe that this part is written in assembly to make things faster. And making things fast is the theme of today, but we'll get to that. So yeah, it seems like there are two flavors of if-then-else based on whether you have an integer that is signed or unsigned. And the code was using the wrong version. So that was the crash. And JSFX, of course, does bounds checking on memory access. It's necessary for JSFX to not crash like that, which is a desirable property when you are messing around and playing around with JSFX. You don't want REAPER to crash. And I guess that is one of the reasons why memory access may be somewhat slow, because it's doing bounds checking and it is doing that at runtime. When your effect is running, it is going to check the boundaries when you are accessing memory. And it cannot do that beforehand as a pre-processing or compilation kind of step. It has to do that while the effect is running. So every memory access has a little bit of cost to check the boundaries. Yeah, that is, I guess, a perfect segue into what the main course is today, the main dish. So it's a new year, and we may need to take a new direction on this library that we are developing. So in case you're new here, we are developing this library that is going to come with a design system, but also some algorithms for processing audio, things that you typically need like filters and convolution, that sort of thing. So usually when you're doing digital signal processing, you need some algorithms, and very few of them come with JSFX. It's a very bare bones language. So we are implementing some of these algorithms to help you develop audio effects more easily. Now, the approach that I'm taking is somewhat different from the approach that everyone else takes. When developing a library, I'm creating abstractions, right? So instead of diving deep into filter design and implementing the filter equations yourself, I implement the filter equations for you, and you just call my functions, and then I can hide from you some of the complexity of implementing the filters. For instance, I can hide from you the filter coefficients, I can hide from you the previous inputs and outputs that are necessary to compute the output of the filter. So I can hide all this detail from you. And that's a good thing. Abstraction is a good thing. The bad thing is usually abstraction costs. It is typically slower to call a function than to just run the code that was in the function body. And it is more expensive to do a loop than to copy and paste a lot of code. Typically, not always, but most commonly. And we are taking an approach in this library that costs a lot in terms of performance. There is a trade-off. So the thing that I'm doing all over the place in this code base is I'm accessing memory. You can see me, the brackets here are memory access, so I'm accessing memory all over the place. And the reason why I'm doing that is so that I can provide better abstractions. So I mentioned how you can use filters by just calling my functions, but the cool thing about the library and the way that we are designing it is that the functions are not the only point of abstraction. I also implemented this sort of objects. It's not really objects, but for all effects and purposes, it is. So a filter is a value that you can put in an array, and a filter is a value that you can pass to a function. A filter is a value that you can return from a function. And that is great in terms of flexibility. If you want to have one filter per channel, which is a very common thing, you want to filter all the channels, the left channel, the right channel, and if you are in a 5.1 setting, you want to filter all 5 channels. In all those cases, you can just have an array of filters that are these objects. Great for flexibility, but not so great in terms of performance. And I mentioned how what we are doing is not typical. What usually people do is they use these pseudo objects. These are these little dots here, not the underscores, but the dots are these namespaces, but they are also pseudo objects, and they're faster because they don't really access memory in the same way. The downside of these pseudo objects is that they are not values, so you cannot pass them as arguments to functions. You cannot return them from functions. You cannot put them in arrays and that sort of thing. So if you want to use these pseudo objects, which will make everything faster, you end up having to write code that looks like, I'm gonna go to req, just because we had just seen on the show recently. But over here, for instance, in the SVF filter, you end up with code that looks like this when you're using pseudo objects. You have to copy and paste some things because you cannot put the filters in an array and loop over the array. Instead, you have to just copy and paste a lot of code. And this is something that happens a lot. See, here, there, and even code like this is sort of copying and pasting. You can see the similarity between these lines and these lines. and then the lines over here, and so forth. So the trade-off is flexibility versus performance. And we are working on the library thinking, forget about performance in the first place, let's just do things that are flexible and nice to use, and then we'll worry about performance. But I think that now is the time to worry about performance, because we are almost at the point where we have some effects, or at least one effect, using the library. And I'm not really sure that this is the right approach to take this. So what we are doing today is first writing a stress test. We are writing an effect that is on purpose going to make things very slow, but not because it is doing something wrong. We had performance issues in the past when developing some parts of the library because of bugs. But we are going to just write something realistic that is going to take a lot of CPU. And then we are going to re-implement that in a different way, and we are going to measure the performance, and we are going to determine whether this approach is going to fly or not. If we should keep pursuing this memory approach, or if we should switch to a different approach. And this different approach that I'm thinking about is not quite the same as just copying and pasting code. It's a bit different. It's a little bit weird. I don't think there is a lot of people doing that, but I think it's going to be fun. And okay, so in terms of what is this realistic effect that I'm thinking about, I was thinking about just using maybe the SVF filters, simple filters, EQ kind of thing. But we're going to have 100 of them. And 100 filters, I think, is somewhat realistic. If you have like a high pass and a low pass, and that's 2 filters, in maybe 10 channels, that's already 20 filters. And if you put some bands here and there, then you can easily get to 50. And if you want to maybe have steeper low pass and high pass filters, then you need to cascade. So having 100 filters is not unheard of. So I guess the effect that this stress test is going to be 100 SVF filters in a cascade. And of course, we can tweak that number. If 100 is not enough, we can go higher, or if 100 is too much, then we maybe can go lower. And so we are going to have 100 filters in a row. And I was also thinking about doing something absolutely bananas as a second test. So maybe let's start writing these things down. So the first one is 100 filters in a row. And the second one is, it goes like this. So check this out. This idea is absolutely crazy, but there is a constraint in how we manage memory. I mentioned how my library is using memory a lot. And there is a constraint in how you can use memory. You can only allocate memory. There are these functions that allocate memory. For instance, this function over here. And you can only call this function from the init block. Under unusual circumstances, you maybe could call this from the slider block, but that would make a click. You would not be smoothly automating the parameters. In any case, and we didn't even run into that while developing our prototypes. Not yet, anyway. But you can allocate memory only in the init block. So you have to allocate ahead of time. And this makes sense. When you're developing real-time audio effects, you are talking about running a piece of code 40,000 times a second. So allocating memory is not something you want to do in the audio thread. And the reason is that to allocate memory, you need to acquire a lock. Typically, most memory allocators are based on locks. And if you need to acquire a lock, the lock may be locked by someone else, it may be busy, and then you have to wait, and then you drop the frame and you hear a click. So allocating memory in the audio thread is a big no-no. That means that we need to know all the memory that we are ever going to use in the init block. And in some cases, you don't know how much memory you're going to use, so you just estimate pessimistically. Just allocate as much memory as you are ever going to need forever and ever pessimistically. So if you think that you may need 100 or 200 slots of memory, then you allocate 300 just to be safe. And that means that we know what is the size of the memory, right? So there are some people playing a trick. Justin talked about this in our stream together a couple weeks ago. So he implemented this filter, but this is not the SVF filter, it's a different filter. It's used for anti-aliasing, but the point is, to implement this filter, he started implementing it with memory, and he was looping over memory locations. You can see here, just inputting the coefficients for the filter in memory. You can see the brackets. But then, this was somewhat slow. Using memory was somewhat slow. Looping over memory is somewhat slow. So he re-implemented this. It seems like a very painful process. He did it by hand. So he re-implemented this using variables instead, because he knows how much memory he's going to need. I guess in this case, it's 64 slots. So he just has 64 variables. And the way that we implemented this thing called a circular buffer is we have a pointer into the array that we move around. So we move a pointer. But he instead is just shifting all the variables around. So to scroll the window, you just assign 64, 63, 63, 62, and so on. So you are shifting the window around, and then B0 becomes available. B0 is going to be your next slot in this sliding window. And this is surprising, because doing all this work, you're shuffling stuff in memory, not in the big chunk of memory that we have access to, but this is still in memory. This is in the stack probably. So you're shuffling these variables around, and still, Justin said that it was probably a 2x or even more of a performance improvement by doing this. So here's the crazy idea. I combined the two ideas together. The fact that you have to pre-allocate all your memory in the init block, and the fact that even doing this is better than accessing memory. So what if you don't have to use memory at all? What if you just write a program where you will not see this character? You're not accessing memory at all. This is something that we can do. And it doesn't matter if we need 64 parameters or 64 values, or if we need 5,000 values, like for drawing a waveform, I think we have 10,000 values. We could have 10,000 variables. Of course, I'm not going to write this by hand, but we could have 10,000 variables. Would that make things faster or slower? So the second stress test is drawing waveforms without memory. I guess you understand what I mean. So, but drawing waveforms with variables instead of memory. So how about that? So that's the idea. I'm going to have a program where I have 1,000 or 5,000 or 10,000 variables instead of using memory. And is that going to be faster? I don't know. And if I will be as shocked as you if this pans out. I mean, if it's faster to have 1,000 variables than to use memory, I will be shocked. But yeah, so that's the plan. 2 stress tests. And I think that with this, we'll be finally able to determine what approach we want to take in 2022. So let's start with this one, because it's relatively straightforward what we need to do. So I'm going to call this the stress test. Maybe I'll call it the stress test filters. And this is going to be using objects. Okay, so I'm going to rename this file. And then I'm not going to implement sliders or anything. I'm just going to go ahead and import my library. And in the init block, I will initialize the library. And we do usually have a slider block, but I don't have sliders for this. And then we usually have a serialized block. And then we have a sample block and a GFX block. I don't really think I need graphical user interface for this one. And I don't really think that I need the serialized. That's just to make the number of channels available on the init block, but I don't think I need that. So I will have a constant here called number of filters that will be 100 to begin with. And then we are going to put all of this in an array. So let's create an array. We'll call this the filters. And photos and stuff is here, and you changed your avatar. Nice. Looks nice. Good job. And you say, hey, Leandro, do you like my new avatar? Yes, I do. And hello. Great to have you here. We are about to write some crazy code. I think you're going to like it. All right, so this size, I guess, is just the number of filters. So I guess I'll just put this here. And then we loop. We start at -1. And then how many times do we want to go around? Well, that is in the size of the array. And then what do we want to do? Well, we want to go into the filters, into the data portion of the filters. And well, I guess I will need a filter, so I'll start here with a filter, and then I will put it there at this location. Now let's go to the SVF part of things. Create a new filter and configure that filter. What is the type that we want to use? We'll have a low pass. And then the low pass will be at 500 Hertz. The gain doesn't really matter for a low pass. So I guess we have an undefined constant, don't we? Yes, we do. And then the Q, I guess we can leave it at that. And this is, I guess, 1 over the square root of 2, which gives us no ripple on the passband, but this is a low pass filter, so I don't think that the SVF equations even use this value. Do they? Let's see. SVF. Oh, did I implement the low pass? Yes, I did. Okay. So we use the frequency and the sample rate, and we do use the Q. Okay. So I think that this configures the filter all right, and then we put it in the array. So now we have an array of 100 filters, and we have a simple location where we can change this number if we want. I'm only going to use the left sample, so as I need another one of these loops. And then instead of doing that, to get a hold of the filter, I will do this. So my sample variable here is SPL0. In fact, I don't need to do it that way. Here's what I can do. I want to apply the filter, right? So I have already configured the filter. Now to actually use the filter, I call this function with the filter and a sample. And I'll just call it SPL0, and that is going to return a new sample that I'm going to assign to SPL0. So this implements 100 filters in a row. If every filter has a 12 dB slope, then this is a 1200 dB slope. Cool stuff. Let's see if this works. I am going to make sure that no outputs are going out. And then I'll load my stress test. Do I need to refresh? Yes. Okay, and it is using some CPU and it didn't crash, which is great news. Then I will add some Burton EQ curve analyzer. Just make sure that we have a low pass going on. And we do. It is a low pass and it is steep, right? Let's see. I'll leave this right about here next to me. And I will edit this so that we don't have 100, we only have 10. Yeah, and then this is less steep. If we have 100, then it's steeper. And then we can play around with this number. It's taking 3% of the CPU to do 100 filters. What if we do 1,000? It's taking about 16% of the CPU. 30% of CPU. That's what I'm looking for. So this is a good, it's a stressful event for REAPER. I don't think it's dropping frames. I think that it's managing. Great, that's what I wanted. So that's stress test number 1. Done. And we'll get to this later, right? I'm going to get... Oh, my voice is glitching again? Did it stop now that I... Okay, back to normal. Okay, so it was probably because I was doing the stressful thing, right? I was running the stress test, but I stopped it. See, no effects on the track. So it was probably because of that it was glitching again. But thanks for letting me know. And I did downgrade black hole. Okay, it only glitched when I opened the filter in REAPER. Yeah, I guess that's the nature of the game when you're streaming and you're stress testing stuff on your machine, right? And I did open an issue on the black hole repository because I downgraded black hole and then I tested and it was working. So I think that the issue last week really was me updating to 0.3.0. But the thing is, it's hard to reproduce. I gave all the information I could, but I don't really know how to reproduce the error. And it wasn't really a glitch. It was more like dropouts. At least that's what I gathered from rewatching the stream from last week. So weird stuff. But downgrading to the previous version, which I guess it was black hole 0 to 10. That version is the one that I'm running right now, and it shouldn't be glitching, except for when I am stress testing stuff on my machine. It shouldn't be glitching. Right. Yeah, okay, so great new avatar. I'm a fan of crazy experiments. You are in for a treat because I'm about to get to the crazy part. Even if I'm not good at coding, I think that if you are watching this and you're following along, you are good at coding because I'm doing crazy stuff. Yeah, okay. And the glitch is probably because of the stress test. Right. So let's write the crazy stuff. And that's the title of this stream, right? The JSJSFX. What's this about? I sort of hinted at this several times before, but let's really get into it. So what I'm going to do is I'm not going to use memory and I'm not going to use loops even. I am going to essentially copy and paste a lot of code, but I'm not going to copy and paste the code. I'm going to write a computer program that is going to generate this computer program. It is a technique sometimes called meta programming. And that's what we are going to get into. It's related to macros, in case you have heard of those. It is related to preprocessors, transpilers, all those sorts of names are going to ring a bell. And I'm not the first to explore this. I should mention, I forget the name. I think it's JSFX preprocessor. Yes. So our good friend of this stream and creator of many amazing JSFX, Giant Love, created this library that is extending JSFX. So it's giving features that really don't exist in JSFX. For instance, structs, which is something that we do. And we are doing structs in the language. We are doing structs in JSFX. What Geraint is doing here is not that. He extended the language. He created another language that has this feature native built in, and then his preprocessor outputs code that looks like this, which is really JSFX. And this myStruct situation turns into numbers just like this, right? And it is using memory, all right? And it's similar in nature to what we are doing, but it's a different approach. You write in this other language, which is, I guess, extended JSFX, and then you run this preprocessor, and the preprocessor outputs text that is really JSFX that we can load into REAPER. And then there are all these other functionalities, including this sequence templates. And if you want to have a bunch of variables with certain names, you can use this syntax, which is not JSFX syntax. It's this extended language syntax. And then it's going to spit out, this preprocessor is going to spit out this kind of code. And the preprocessor approach is very common, and it's very nice because if you know JSFX, you can just learn the extensions. And that's great. But I decided to not go with that. And the reason is that you now have to learn this extended language, and that's a very niche thing. There are some people who know JSFX. It's a small club, but there is a club. And then there is an even smaller club who knows these extensions. And I suppose that probably Geraint is the only person using this library, as far as I know. I don't know any other JSFX using the library, is using this preprocessor. So, and I guess it's also kind of a lot of work to extend the language in these ways. It's a lot of work to do it in the first place, to implement the parser for this, to implement the code generator, and to implement maybe some error checking, all that good stuff. And then even if you do it all right, you still have to do a lot of work to document all this, like writing this documentation, and then you have to do more work to convince people to learn this. It's a lot of work to extend the language that way. And even then, you don't get something that is absolutely super powerful. For instance, what is the syntax if you want to have full -1 here? If you want var1 to be 0, var2 to be 1, and so forth. I don't know if there is syntax for this, but judging by the documentation, it doesn't seem like there is. So this is the kind of thing that we are interested in. We are interested in collapsing this copy and paste into a block of code. But I don't think that doing it this way is my preferred way. What I want to do instead is write a program in JavaScript that produces text. It's just a big old program concatenating a lot of strings, and the output of the program, the result of concatenating all these strings, is a JSFX program. Why do it that way? Well, because there is a small community who knows JSFX, but there is a big community who knows JavaScript. And then if you happen to be in the intersection, which I guess many people are, even if you're not a JavaScript developer by heart, you still are able to read and write JavaScript, especially because it's similar to C, and JSFX is also similar to C, so they all share this common hierarchy, this heritage. So I'm going to write a JavaScript program that generates text, which is JSFX. And I'm going to collapse the repetition in the JavaScript program. And then I will not have my real objects. I will not be accessing memory all that much because I will be extracting as much as possible into the JavaScript part of the code. In fact, because I will be using JavaScript that way, I can get away with not using some of the JSFX abstraction mechanisms. For instance, the functions. This is actually a very nice conversation to have. Yeah, JavaScript, JavaSonic. Yes, I'm putting the JS back into JSFX. When I first learned about JSFX, I was like, oh, I can write real-time audio effects in JavaScript? Yeah, that's awesome. No, it's a different language, which is still great. But we have to have a conversation about this language. It has a super, super nice property. JSFX has a super nice property that I think we can leverage in a smart way. The nice property is something called Turing Incompleteness. Let's talk about programming language theory for a moment here. Most programming languages that you have heard of, like JavaScript and C and Java and C++ and Python and Ruby and Go and Rust and many others that you have heard of, they are characterized by being Turing complete. What that means is that any program that a computer can compute, which is not all programs, or which is not all problems. So any program that a computer can compute, any program that a computer can run, can be translated between any of these languages, and they are equally powerful in terms of being able to express that problem. So let's put this in more plain terms with an example. Suppose that you write a program that is going to compute the sum of all the numbers up to 100. So if you write that program in C or in Java or in C++ or in Ruby, in all these languages, you can always translate this program into all the other languages. And the same is true of any program you write in any of these languages. And of course, if you're doing real-time audio effects, you're probably going to do it in C++. And if you are developing a web application, you're probably going to do it in JavaScript. So there's a lot more libraries and infrastructure around that. But the principle of being able to compute, being able to manipulate numbers and strings and memory, all of that can be translated into any other language. So anything that a computer can do can be expressed in any of these languages. They are all Turing complete because Turing completeness is this property of being able to represent computation. And all these languages are equivalent in terms of being able to represent computation. Turing complete languages are awesome. We use them all the time and they're great. But there is something to be said about Turing incomplete languages. What's that about? Well, a Turing incomplete language is incapable of representing some computation. There are some programs that you can write in all these other languages I mentioned that you cannot write in JSFX because I don't really have a mathematical proof of this, but I have a very strong intuition that tells me that JSFX is Turing incomplete, and it's Turing incomplete by design. So what's that about? Why do we care about this? Well, Turing complete languages, they have a fundamental flaw. There are some things about these programs that you cannot determine. And all of these problems are sort of equivalent. You can reduce one of them to the other, but I will use the most common example of something that you cannot determine in a Turing complete language. Given a program, any program, can you tell if this program is going to terminate or not? Is it going to loop forever? Or is it going to output something? Or is it going to run into an error? You cannot answer that about any program. Right? I can always come up with a crazier program that is going to defeat whatever strategy you think of to determine if a program is going to terminate or not. And that is a fundamental characteristic of Turing completeness. If you want to be able to compute anything in the computer, you will not be able to compute some other things. In particular, you will not be able to compute some things about the computer itself, like, is this program going to terminate or not? There are excellent videos on YouTube explaining why that is the case and showing you proofs of this property called the Turing Incompleteness of these languages, or the Turing Incompleteness theorem. It's a great little nugget of knowledge. But the thing is, if you cannot determine that something is going to terminate, in some cases, that's a bad thing. If you're doing real-time audio processing in a sandbox kind of thing where you don't want REAPER to crash, your program may be slow, your JSFX may be silly, and it may be glitching the audio on the stream, but it will not or should not crash REAPER, except when there is that bug that we talked about in the beginning of the stream, but that's an exception, right? It is supposed to be the case that JSFX never crashes. You can divide by 0, you can take the logarithm of negative numbers, you can run loops that don't really have an end boundary, you can do whatever. JSFX is always going to find a way out. If you divide by 0, it's going to say, okay, the answer is 0. If you have a loop that doesn't terminate, it's going to say, okay, after 1,000,000 times I'm done, I'm going out of this loop. Doesn't matter. JSFX always finds a way out. JSFX is Turing incomplete because all JSFX programs terminate in some sense. And if you think about the program being like this loop, then it is always the case that this sample block is going to terminate. You are always going to reach here. You're always going to reach here. If your loop is over a big number, JSFX is going to ignore your big number and stop at, I guess, 1,000,000. If your program divides by 0, it is going to, if you do something like this, it's going to say, okay, the answer is 0. It doesn't matter. It's just always going to reach here. And it has to, because it doesn't want to crash REAPER or hang forever or whatever other bad scenario. So by virtue of this, REAPER can give full control of the CPU and all the processes to JSFX with the certainty that it is going to terminate. And then the language has all these weird quirks to make sure that it's going to terminate. See, there is a limit to the number of times that this is going to loop, and it is around 1,000,000. And so because this is Turing incomplete, we do have some things that we can say about JSFX. The programs always terminate in some sense. You always get to the end of this and you are able to come back around. And another source of looping that could make a program not terminate is functions. If you have a function that calls itself, it could be calling itself forever. It's a kind of a loop. You can always transform functions into loops and loops into functions if you want. But in JSFX, they have an answer for that. You cannot call a function that has not been declared before you. So if you want to call a function, it has to be declared above you. So if I want to call a function anywhere, like I call a function here inside another function, that's all right, because this function definition is before this function definition. There is a strict order to the function definitions. You can only call functions that happened above you. You cannot call yourself. If you tried to call yourself here, JSFX would say, oh, I have not been defined yet, not fully anyway. And in all the Turing complete languages I mentioned, from C to JavaScript and so forth, they all have this notion of calling yourself. So you can, when you declare a function, there is always a way for you to call yourself. This is something called recursion. JSFX does not allow for recursion. So yeah, all these sources of not stopping or all these sources of things that could halt your program or could loop forever, they have been stripped away from JSFX. What that means is that when we are writing our JavaScript program that generates JSFX, we can define functions in JSFX. We can output text that looks just like the thing I highlighted. But let's think about how this function is actually run. Well, because functions cannot call functions above them. If I want to have a function call here, the function definition has to have happened already, has to have happened above. You could, in theory, anytime you see a function call, you could go to its function definition, and let's pretend that this is the function definition. It isn't, right? It's a different name, but suppose that this is. So you could just copy and paste the code here and inline the function. Now, you do have to make sure that your local variables are not going to conflict, because what used to be local variables are now global variables. So you have to be smart, and you have to label these function calls with something like call1, and you have to do that for all the local variables. And you have to do something like this. And then if you call the function again, you have to copy and paste the body of the code again. And then you have to make sure that you rename this to something like call2. And you have to come up with unique names for every function call. But this allows you to inline the function in such a way that the definition of the function becomes unnecessary. You can just remove it. It has been inlined. This sort of inlining is something that happens in compilers that try to help you run your code faster. When compilers are looking at function definitions and function uses, function calls, it checks if the function definition is somewhat small and somewhat near, and there are all sorts of conditions for this to happen, but it inlines the function body in exactly pretty much this way. And from our measurements way back, this is not the first time I have been exploring the issue of performance in JSFX. When we did our last stream exploring this, I guess 2 months ago or something like that, we learned that when we inlined some function calls, things did get faster. I think it was like a factor of 2, but we were talking about small numbers. So it went from like 2% CPU to 1 or 1.5% CPU, something like that. So inlining functions is another thing that makes things faster. So because of the way that functions behave in JSFX, and because of the Turing incompleteness of JSFX, we can pull off something kind of cool, which is to not have any function abstractions at all in the JSFX portion. We can just inline everything. In other words, our plugin can be as fast as JSFX can run something. And I suppose that whatever optimizations Justin is doing on my code before it runs, right? For instance, the ARM thing that we talked about in the beginning of the stream, that's sort of assembly. So I think it's an optimization. It's something that runs really fast depending on your architecture. And whatever they are doing there, I think it will benefit from the inlining that I do, because then they don't have to do any inlining on their side. They don't have to make their compiler faster on that aspect. So I think this has the potential of being not as fast as other effects like the req effect that is using copy and pasting. I don't think that it can be as fast as this. I think it can be faster. I think it can be faster than the thing that claims to be as fast as JSFX can muster. Almost, because I think we can be faster. We'll see. We'll see. And another thing is so what we are going to do is to re-implement this program using this other technique. I'm calling this technique JSJSFX because it's JavaScript generating JSFX. And we are going to see if it's faster, if I can deliver what I'm promising. And also, we are going to see how ergonomic this turns out to be. Because I think it will be somewhat messy. But we'll see. We do have a big language. JavaScript is a big language. Lots of abstractions. You have classes, you have functions, you have loops, you have variables, you have lots of things. So we'll be using a very high-level language to do this. So I think we'll be able to write nice abstractions that will clean things up in a nice way. But we'll see. We'll see if the cost of learning JavaScript to use our library is going to pay off in terms of performance, but also in terms of how the program is going to look like. So I'm very interested in knowing if this program is going to be better or worse to look at than this. because I will be the first to admit, this is nice because it gives me all the flexibility I want in terms of managing multiple channels and putting things in arrays and all that good stuff that you mentioned, but I don't like to look at this. This is terrible code. Lots of repetition, very noisy. It's hard to make sense of what's going on. So in JavaScript, we have better abstractions. Does that pay off? I don't know. And if we develop the library using this concept, it's not just a library now. Now it's a whole approach to how you were supposed to develop JSFX. Is it something that is worthwhile? Do other programmers in this space want this? I don't know. We'll see. That's the experiment. And there's the flash of programming is faster than the speed of light. We'll see about that. And Noel Parson is saying vorg.ong. Thanks for being here. I will report you real quick. And then we'll be out of our way. Okay. Yeah, so crazy stuff. Let's write some JavaScript, shall we? I think I'm going to start by going into this folder and I'm going to install check this out. Arya is here. Hello, Happy New Year, Merry Christmas. How are you doing? You are alive. Are you well? I hope that you are well. Do you want to get back to streaming together? Right. Okay, so Happy New Year. So let's install something that is a JavaScript library. And what it does is it just listens for changes in the file system and reruns a program. So I am going to create something that I just call it index.js. And I'm going to put here a script called start that runs nodemon. It's node monitoring. Node is a runtime for JavaScript. It's a way of running JavaScript in the command line as opposed to running JavaScript in the browser as people usually do. So node runs JavaScript in my machine or in the command line. And then I can monitor for file changes. So I can run index.js. And then let's see how this works. If I run npm start, it is running that file, and then it has a clean exit because this program is empty. But anytime I save, you can see that it runs the program again. So that's pretty much all we need. So I guess another thing I'm going to do is in this package JSON, I am going to say that the type is module. So I'm using the newer ECMAScript modules, and then I'm going to import fs promises, and I'm going to await on fs write file, and this is going to be a file called liafac stress test filters JSJSFX.JSFX. And then I can write anything in there. For instance, I will write hello. And then see, because I saved this index.js file, this other file key here came to life, and it has that content. So I can start writing JSFX in here. Let's write something that... Let's write a description. I guess I will do it like this. So this is liafac. Well, it's pretty much this. Oh, but I forgot a column, just like that. And then I saved, and then bam, it's there. So because of this nodemon infrastructure and whatnot, writing this code feels like writing JSFX directly, because anytime I save, I can just jump into Reaper and it will be there. Now, naturally, if I go to Reaper and edit the effect in the IDE, then I will need to come, well, first of all, the program that we generate is going to be a mess. So debugging that is going to be horrible. But also, if I make any changes to the generated JSFX, so if I come in here and I am in the Reaper IDE and I change something to say that a is equal to 1 and I save, then let me put this side by side. So anytime I come here and I do another change and save, then my changes over there are lost. So yeah, it's kind of ergonomic, but it's not perfect. And I will have to create a .gitignore in which I ignore node modules. Then I'm back to 5 changes. And all of this that I'm doing is in the directory where I have my Reaper effects. So I wonder if this null modules with hundreds of files in there is going to make Reaper trip, but I suppose not. I suppose it will be fast, but let's see. If I go to my effects browser real quick and scan, yeah, it's okay. It's not bad. So then we can load our Liafak. Then, yeah, okay, there is a lot of junk in here. We'll have to fix this. But whatever, it's good enough for now. Stress, JSJSFX, and there are 2 of them. What's that about? Is there a way for me to show the path? Oh, I guess it's reading the JavaScript file as JSFX. Okay, that's not a good idea. So we probably want to move all of this somewhere else. But whatever. Right now we have our effect and it has its description right there. Good enough. Let me start by addressing this fellow. So your Henry Singleton report. Did I get the right person? I don't want to report the wrong person. Put easier in timeout, remove, hide, report, unwanted, thanks. Okay. I was on an island, didn't know, doesn't have internet. Okay. Yeah, let's start Wednesday, sure. Okay. Are you making something to what you did on my website, write in JavaScript and generate? Yeah, it's similar in spirit, yeah. In any kind of web server or any static website generator, in the end of the day, it's a big old program that generates HTML, CSS, and JavaScript that goes to your browser. So in essence, it's a big old way of concatenating a bunch of strings and generating a program out. And and HTML, CSS, and JavaScript is a programming language. So what we are doing, and people do this, like they write Ruby servers that generate HTML. They write Java servers that generate HTML, Python servers that generate HTML. What we are doing is we are writing JavaScript that generates JSFX. It's a similar thing in spirit. And okay. There is a path column in the effects browser. Right click and check it. Yeah, okay. Showing effects list, file names. Okay. I don't think I need it. Because if there is 2 effects with the same name, then it shows one of the file names, which is good enough for my purposes. And then over here, oh, that's nice. Didn't know that. Okay, so scrolling to the right, I guess, is, oh yeah, I have more stuff to the right, but yeah, the file name here is good enough for me to differentiate, and I will move this out, but not right now. So let's try to write something. Where do we even start? Well, to do the SVF, we need all these things. So I guess I'm just going to start by hard coding some things. Yeah, I guess I will hard code the coefficients. Yeah, okay, let's split the screen. I'll leave my reference on the right, actually. This way I'm sure that I'm not on top of whatever I'm writing. So we'll need a type. Well, it's kind of silly to have a type because I'm only going to implement one of the types. Then we need a frequency, and that is going to be 500. We need a gain. We don't use that in a low pass. Then we need a Q. That's going to be that. And then we need A1, A2, and blah, blah, blah. So let's go to the part where I actually compute this. Just like that. And then the frequency is set. The Q is set as rate exists. 10 comes with JSFX. This is using Q. This is using variables that have been previously defined. Okay, so I think that this is all we need to compute the coefficients. Then let's go to where I am using the filter. So we do need, oh yeah, I need a section, right? So all of this is going to be in the init section. I'm just initializing things. And also in the init section, I guess I will initialize these variables. But they initialize to 0, so it is kind of silly, but I will initialize anyway. So I'm going to separate this into the part where I'm setting things up. This is like the inputs to the filter, or the configuration of the filter, I should say. This is the internal stuff. This is, well, more internal stuff. So this is the internal stuff that doesn't change. This is the internal stuff that changes. And then to compute the filter, I do something like this. Okay, let's see. This sample coming in, well, first of all, this needs to be in the sample block. And the sample is just SPL0. Then all the rest is fine. So I'm just going to say that SPL0 is equal to the output. So let's see, if I just run this, I think it should work, and I think it should give me a low pass filter. Let's put the good old Burton EQ analyzer. Oops, no, not like that. Drop that guy here, copy and paste, put the stress test in the middle, and we have a low pass filter. Great, now we just need 100 of these. Let me commit what I have. So this is the part where you would start copying and pasting this. You would say, I see one EQ, I see two EQ, and the V's and the output and all of that. We would start we would either have a function or some sort, or we would start copying and pasting this. Like I see one EQ for filter 1, for filter 2, and so forth. I think I'm going to remove this from here just to make things simpler. And now I am going to use the power of JavaScript. I am going to have a loop that is going to run for 100 times. Okay, what the hell is this? So I am in this string. This is just a string, okay? I said that we would be generating JSFX by concatenating strings. This is a way to write strings in JavaScript. You can use double quotes, but you can also use backticks. And the cool thing about using backticks is that you can pop out of the string and write some JavaScript. This is exactly what I'm doing here. I'm creating a list of 100 elements from 0 up to 99. Oh, actually it should be 1,000, shouldn't it? In our stress test with objects, we are doing 1,000. So we are doing 1,000 elements in this list. It just goes from, let me show that in the console real quick. See, it's a list of 0 up to 999. And then I'm mapping over to generate some JSFX. I will write some JSFX in here. And then I'm joining that list, all the elements in that list with a new line. So it ends up looking like this. And this is going to be, this string that comes out is going to appear at this point in the bigger program. So what is the JSFX that I want to write? Well, it's pretty much that. And maybe I don't really need this sample stuff. I can just use SPL0 and my output is going to be SPL0 as well. Okay, so right now I have 100 copies of this blob. Looks like this, but it's just using the same variable over and over, the same v0 over and over. That's no good because we want the v0s to be different. These are independent filters. Yes, the input to the filter and the output to the filter are cascaded, but they are independent filters. They are independent v0s, so they should not have the same name like this. So what I'm going to do is for all the local variables, I mentioned before how we would sort of extract this into a function. Well, it's not quite a function, but we are inlining that function call, so to speak. So I guess what I'm going to do is for all occurrences of v0, I'm just going to prepend v0 with, or prepend or append. I guess I'm going to append v0 with my index. And then v3, same deal. In fact, wouldn't it be nice if I copied this, right? And then occurrences of this variable, and then occurrences of that variable. And then A1, we don't change. That's a coefficient. That's the same. It can be shared. It doesn't really matter. Then all these guys, then V2 needs to be different. And then SPL0 is the same and M is the same. It's just over here at the coefficients. So now when we save this and we go to the source that is generated, you can see that the variables here are different now. They are independent filters. V03 is not the same as V04. And yes, it is valid to have namespaces with dots and then just numbers like this. So now this is 100 filters, or not 100, this is 1,000 filters. And we are not even using functions. This is as fast as I think JSFX can be. I hope, we'll see. And my audio may be glitchy as soon as I do a full compile reset now. Yeah, is my audio glitchy? I think it is. Is my audio better now? I think it should be. But we saw that it was about 20% CPU instead of 30. So not bad. It's not like a 10, it's not an order of magnitude. It's not 10 times better, but it is better. And Daniel is here. Hi, great to have you here. So yeah, the audio was glitching, but it's not anymore, right? So in essence, Yeah, it glitched for a few seconds. Okay, that's expected, but it's back now. So the black hole situation has been fixed. Great. So this is fast. This is faster. It's not an order of magnitude faster. I was expecting kind of an order of magnitude faster, or at least 2 times faster, but it was only about a third faster, which is still faster. It's not bad. And the kind of code that we were able to write here isn't that bad either. I guess we could have something like, what about we had something like this? Now I'm just kind of nitpicking how I am writing this code. It's not a major difference, but whoops, no, that doesn't work. Okay. What's up with that? This, and then that, and then this. And then I don't think that variables in JSFX can start with a number. So I'm just going to real quick take the index and generate a string that reads like local underscore underscore index underscore underscore. Yeah, I think now I'm just nitpicking how I'm doing this, but there is a fundamental change that I'm applying to this. So I'm changing the way that I'm writing stuff, because I think that writing it like this is not too bad. I'm just prefixing stuff by saying, okay, this is going to be a local variable. And we could even be maybe cleverer and come up with something a bit different to make this read even better. But the point here is I'm making all these variables local variables, just like this, but I'm also putting underscores instead of dots. And I'm not sure if the namespace, the dot is a namespace and it generates a pseudo object. I don't know if that's free or not. I tend to like the dot instead of the double underscores, but maybe they're not free. So we are going to glitch the audio again for a moment to test this hypothesis that this is going to make things a bit faster. We'll see. It doesn't seem to make any difference. So using the dot is acceptable. It seems to be free anyway. Okay, so there you have it. This is the first part of the experiment. Tomorrow I will be doing the second test, which is an even crazier test, which is the drawing of the waveforms using variables. So we are going to apply the same technique, except that we are going to do something similar to what Justin did on his fur filter in ReQ. We'll have a bunch of variables like this, and we'll slide the window just like that, and we'll see if that is faster than accessing memory for a big window. This is a window of 64. We'll do a window of 10,000. And we'll see if that's better. And just want to point out that writing code that looks like this is not too different from the library that Geraint created. There is some notion of initializing a loop, just like this. There is some notion of names that you have to replace, just like that. And the advantage of doing this outside the language, we're not doing in this JSFX extended kind of thing. We're doing this in JavaScript. The cool thing about doing this is that we have the full power of JavaScript at our disposal. So right now we don't have a lot of in terms of abstractions here, but we can write functions, for instance. I think that the notion of looping over things like this is going to be something that comes up often. Also, another thing is there are these snippets of code that are actually related. Right now, this is all there is to the effect, but suppose that we would want to draw the waveforms for this. We would need to have something in the init block for initializing the waveforms data structure, and then something in the sample block to collect into the waveform, and then something in the GFX block to actually draw the waveforms and all that. So I think that we can use JavaScript to sort of extract and use the principle of locality to make the code even better. So everything related to a feature is in one place. So yeah, using JavaScript may be advantageous because of that. So that about wraps up the reasoning for exploring JSJSFX, this new crazy idea that I'm coming up with. It's relatively straightforward for people who know JavaScript. It is 1/3 faster, as we just measured. It is super powerful. Maybe it's good. I don't know. We'll see. Tomorrow I will be back here at 6:30 UTC and we will do this other effect. Thank you all for being here, Fotis and Daniel and Bo and Arya and everyone else who was just lurking around, and even the spammers who were sending nonsense on the chat. I appreciate you all. You are just trying to con people and make money. I cannot judge you. We all sometimes try to steal money from someone else. Isn't that right? Right. I see you tomorrow. Thanks for being here. Bye.